The 7 categories of additive manufacturing, ISO/ASTM 52900:2021. A. Solid-based additive manufacturing technologies. 1. Material extrusion MEX. Fused deposition modeling, FDM. Fused filament fabrication, FFF. Freeform fabrication, FF. 2. Sheet lamination, SHL. The ultrasonic additive manufacturing, UEM. Laminated object manufacturing, LOM. B. Powder-based additive manufacturing technologies. 3. Powder bed fusion, PBF. Multi-jet fusion, MJF. Selective laser sintering, SLS. Direct metal laser sintering, DMLS. Electron beam melting, EBM. 4. Directed energy deposition, DD. Laser engineering net shape lens. Electron beam additive manufacturing, EBM. C. Liquid-based additive manufacturing technologies. 5. VAT photopolymerization, VP. Stereolithography, SLA. Digital light processing, DLP. Continuous digital light processing, CDLP. 6. Material jetting, MJ. Nanoparticle jetting, NPJ. Drop-on-demand, DOD. 7. Binder jetting, BJ. Solid-based additive manufacturing technologies. 1. Material extrusion MEX. Fused deposition modeling, FDM. Fused filament fabrication, FFF. Freeform fabrication, FF. 2. Sheet lamination, SHL. The ultrasonic additive manufacturing, UEM. Laminated object manufacturing, LOM. Material extrusion, MEX. Continuous flow. Imagine a hot glue gun, but instead of flat lines, it builds intricate shapes layer by layer using a melted plastic filament. Precise deposition. A heated nozzle carefully deposits molten material, creating each layer on top of the previous one. Dynamic movement. The nozzle moves horizontally, while the platform moves vertically, enabling complex 3D structures. Accessibility. Affordable and user-friendly, material extrusion is popular in hobbyist and even professional settings. Diverse materials. From common plastics like ABS and PLA to exotic options, a wide range of materials is available for various properties. Fused deposition modeling, FDM. FDM is a material extrusion process where material is heated and deposited layer by layer. It is commonly used in inexpensive 3D printers and requires controlling several factors for good quality. Unlike other 3D printing processes, material is added continuously through a nozzle under constant pressure. Material layers can be bonded by temperature or chemical agents. Material is typically added in spool form. Fused filament fabrication, FFF, also known as fused deposition modeling, FDM, is a popular 3D printing process using continuous thermoplastic filament. FFF printers melt filament in a heated extruder head, depositing layers to build the desired object under computer control. Various materials like ABS, PLA, and nylon can be used for FFF printing, offering versatility in applications. The process involves software processing of STL files, nozzle movement to deposit layers, and thermal control for proper material bonding. FFF printers typically feature a flat bed, gantry system, and stepper motors, with some using 3D printed components and polar coordinates for printing. Freeform fabrication, also known as solid freeform fabrication, SFF, encompasses various technologies that enable the direct creation of complex solid objects from computer models without the need for part-specific tooling or extensive human intervention. It also goes by other names like rapid prototyping, rapid manufacturing, and solid freeform fabrication. The process allows for the creation of complex shapes and structures layer by layer. Unlike traditional manufacturing methods, FF does not require molds or tooling, offering greater design freedom and flexibility. FF techniques include selective laser sintering, SLS, stereolithography, SLA, and digital light processing, DLP, among others. FF is used in various industries such as aerospace, automotive, healthcare, and consumer goods for prototyping, customization, and low-volume production. The process involves converting digital designs into physical objects by selectively solidifying or fusing materials, enabling rapid iteration and customization. Steps: material preparation. The filament, typically made of plastic, ABS, PLA, etc., is loaded onto a spool and fed into the printer. Extrusion. The filament is heated and softened within the extruder nozzle. Deposition. The molten material is deposited onto the build platform, following a computer-generated path. Solidification. The extruded material cools and solidifies, bonding to the previous layer. Layer by layer. The process repeats, building the object layer by layer until completion. Technical info. Advantages of material extrusion process. Utilization of readily available ABS plastic. Ability to produce models with good structural properties similar to final production models. Economical in low-volume cases compared to injection molding. Challenges of material extrusion process. Numerous factors to control for achieving high-quality finish. Limitations due to nozzle radius affecting final quality. Lower accuracy and speed compared to other processes. Final model quality limited by material nozzle thickness. Considerations for achieving high tolerance. Accounting for gravity and surface tension, especially for components requiring high tolerance. Typical layer thickness. Ranges from 0.178 mm to 0.356 mm. Post-processing methods to enhance visual appearance. Improving material transmissivity, explored through methods like increasing temperature and resin use. Experiment with cyanoacrylate resin, resulting in 5% increase in transmissivity after 30 seconds and sanding. Shrinkage likely with heat-related post-processing, necessitating tolerance considerations. Machine example. Machine Instec MX3. Area 1000 by 800 by 650 mm. Layer thickness. Al, cobalt, copper, and nickel alloys. Build volume 520 L. Materials. The material extrusion process uses polymers and plastics. Polymers. ABS, nylon, PC, AB. Advantages. Widespread and inexpensive process. ABS plastic can be used, which has good structural properties and is easily accessible. Disadvantages. The nozzle radius limits and reduces the final quality. Accuracy and speed are low when compared to other processes, and accuracy of the final model is limited to material nozzle thickness. Constant pressure of material is required in order to increase quality of finish. Sheet lamination, SHL. Sheet lamination processes include ultrasonic additive manufacturing, UEM, and laminated object manufacturing, LOM, that build objects layer by layer, but differ in materials and applications. UEM uses metal sheets/ribbons bonded by ultrasonic welding, no melting. Suitable for structural applications with materials like aluminum, copper, stainless steel, and titanium. Allows for complex geometries and internal features. Requires CNC machining to remove excess material. Low temperature process and energy efficient. LOM uses paper layers bonded with adhesive. Limited to aesthetic/visual models, not suitable for structural use. Employs cross-hatching for easier post-build removal. Ultrasonic additive manufacturing, UAM, a hybrid process, combines ultrasonic welding and CNC milling to create solid metal parts. Unlike traditional metal printing methods, UEM doesn't melt the materials. Instead, it utilizes high-frequency vibrations to join metal foils in a solid state, disrupting surface oxide films between metals. This low-temperature technique allows for the joining of temperature-sensitive materials at below 50% of their melting temperature, ensuring minimal distortion. UEM incorporates CNC contour milling to shape parts and introduce intricate internal features, facilitating the joining of dissimilar metals without significant intermetallic deformation and enabling fast build rates. Don White's invention of UEM in 1999, patented and commercialized through Solidica Incorporated, revolutionized metal fabrication, leading to advancements such as improved weld tooling and expanded weldable metal options, including very high-power ultrasonic additive manufacturing. Laminated object manufacturing, LOM, uses a similar layer-by-layer approach, but uses paper as material and adhesive instead of welding. The LOM process uses a cross-hatching method during the printing process to allow for easy removal post-build. Laminated objects are often used for aesthetic and visual models and are not suitable for structural use. uses metals and includes aluminum, copper, stainless steel, and titanium. Ultrasonic Additive Manufacturing Overview, 2014. The process is low temperature and allows for internal geometries to be created. The process can bond different materials and requires relatively little energy, as the metal is not melted. Steps. The material is positioned in place on the cutting bed. The material is bonded in place over the previous layer using the adhesive. The required shape is then cut from the layer by laser or knife. The next layer is added. Steps 2 and 3 can be reversed, and alternatively, the material can be cut before being positioned and bonded. Technical info. Laminating, LOM, is one of the first additive manufacturing techniques created and uses a variety of sheet material, namely paper. Benefits include the use of A4 paper, which is readily available and inexpensive, as well as a relatively simple and inexpensive setup when compared to others. The ultrasonic additive manufacturing, UEM, process uses sheets of metal, which are bound together using ultrasonic welding. The process does require additional CNC machining of the unbound metal. Unlike LOM, the metal cannot be easily removed by hand, and unwanted material must be removed by machining. Material-saving metallic tape of 0.150 mm thick and 25 mm wide does, however, result in less material to cut off afterwards. Milling can happen after each layer is added or after the entire process. Metals used include aluminum, copper, stainless steel, and titanium. The process is low temperature and allows for internal geometries to be created. One key advantage is that the process can bond different materials and requires relatively little energy as the metal is not melted, instead using a combination of ultrasonic frequency and pressure. The Engineer, 2014. Overhanging can be built and main advantage of embedding electronics and wiring. Karunakaran et al., 2012. Materials are bonded and helped by plastic deformation of the metals. Plastic deformation allows more contact between surface and backs up existing bonds. Janaki Ram et al., 2007. Post-processing requires the extraction of the part from the surrounding sheet material. With LOM, cross-hatching is used to make this process easier, but as paper is used, the process does not require any specialist tools and is time-efficient. Whilst the structural quality of parts is limited, adding adhesive, paint, and sanding can improve the appearance, as well as further machining. Machine example. MCR Matrix 300+. Area. A4 paper. 256 by 169 by 150 millimeters. Layer thickness. 0.1 millimeters, 0.19 millimeters. Materials. Effectively any sheet material capable of being rolled. Paper, plastic, and some sheet metals. The most commonly used material is A4 paper. Advantages. Benefits include speed, low cost, ease of material handling, but the strength and integrity of models is reliant on the adhesive used. Krar and Gill, 2003. Cutting can be very fast due to the cutting route only being that of the shape outline, not the entire cross-sectional area. Disadvantages. Finishes can vary depending on paper or plastic material, but may require post-processing to achieve desired effect. Limited material use. Fusion processes require more research to further advance the process into a more mainstream positioning.